Hi everybody, this is the session 5 of the GC surgery entitled of multi-level calibration and ISO10723. This is a recording version of the GC surgery session that was happening on the 3rd of May 2016. So to begin with, I'm gonna start the discussion with the difference between single point calibration and the multi-point calibration. On the single point calibration, the response factor is a function of peak area and calibration gas mole percent. If we plot a chart of the response factor here, it's actually, if we put peak area on the y-axis and mole composition on the x-axis, it basically creates a straight line. And this is basically an assumption that we make that GC have that certain calibration function that it has. So we always assume it as a linear when we have a single point calibration. There are also other types of calibration, such as the exponential calibration response factor, as well as the relative response factor. But what I'm going to focus here is a comparison between the single point calibration against the multi-point calibration. The same principle later on can be applied to compare the multi-point calibration against other type of calibration in the system. So if we plot the multi-level calibration result against a single point calibration result, we can see something like this. So on the single point calibration result, let's say we calibrate it at 75% here. And what it does, it will then create a straight line, which is the assumption of the calibration function that we have. So in any area, let's say we have another peak area over here. Let's say we got that peak area, it will then correspond to 60%. But in actual case, that particular peak area there doesn't really correspond to 60%. 60% will be in that particular peak area there. So the multi-level calibration actually create a curve that is not necessarily the same as a single point calibration curve. So it basically will introduce a bias in the system. Now, the multi-level calibration result is basically the true function and not the assumed function. The assumed function is the single point calibration result, which is the blue line. So what we want to do, what we want to achieve is basically operate based on the true function rather than the assumed function. So in order to achieve that, we have a method called the ISO10723, or this is a standard that's called the ISO10723. So the goal of the ISO10723 is first to quantify the GC repeatability across the whole range, then to quantify the GC linearity across the whole operational range, and then from there, then we can determine the GC performance benchmark, which includes the error, which is the bias that is associated with the non-linearity, and then the uncertainty that comes from the calibration gas that we use, also the repeatability, and then the overall bias, which is a combination of the error and the uncertainty. So I'm not going to discuss too much about the repeatability part of it. So basically, or the uncertainty part of it. Basically, the uncertainty calculation is very, very similar to the session 4 that we have discussed earlier. The only difference here is that it creates a function in the form of a constant, which is what we call a precision factor, as part of the repeatability. So it basically shows us that there's a possibility that the GC will have a different repeatability dependent on the range that it actually operates on. But what I'm trying to show here in this particular presentation is the linearity section and the bias that is introduced by the non-linearity of the system. So this is basically the two topics that we're going to be focusing on today. So what it does on the 10723, ISO 10723, is we perform the test with seven test gases. So ISO 6974 Part 1 2012 actually specify that minimum 7 certified reference mixture should be selected to allow regression curves that are up to third order in nature. Now, the goal here is to create a regression curve that can go all the way to the third order. And the reason for that is like the third order will be more accurate than the second order, and it will be more accurate than the linear one. So that's why we need the 7 certified reference mixture. So here's an example. Let's say we have a methane that range between 60% to 90%. So what we're doing here, we basically try to test the GC on the 60% and 90% and everything that happens in between that. So we got the 7 gases, and then we basically separate this range by 5% in this particular example. So it goes from 60%, 65%, 75%, and it goes all the way to the 90%. And what we do then, we plot the peak area of methane that results from the analysis of each individual gases and plot it against the actual certified mole composition that we have in the calibration gas. So now we basically have a chart of peak area against the mole composition. What we then do is we try to work out what is the polynomial curve function. So we create the polynomial curve function based on the regression that we have on the 7 test gases. Now, in this particular example, we basically have a second order polynomial. So sometimes we basically have linear function, sometimes you have second order polynomial, sometimes we have the third order polynomial. Now, this ISO 10723 actually defines how we can decide which order polynomial curve is actually required. So we can actually work out what is the best fit for the function that we have. Now, when we do this, we basically quantify the nonlinearity of the GC. So basically, we create a true function of the GC performance itself. So that covers the nonlinearity part. Now, there's also uncertainty associated with the nonlinearity function. So what it does is basically, what we're basically doing here, every time we do a test, let's say we do a test on the 60% gas. So what happens is we will get peak area that goes up and down a certain limit. And also, when we do it on this range, we get peak area that goes up and down in a certain limit. A certain uncertainty or repeatability. So what we get is the repeatability, or the average of this repeatability data, and that's the data that we plot here. But the standard deviation that we can actually work out, the 2 standard deviation, or we're using the t distribution, then is going to be considered as the uncertainty associated with the nonlinearity function itself. But again, I'm not going to talk too much in detail about the uncertainty associated with it. I'm going to focus more on the bias or the error that is introduced by not implementing the true function, the true analysis function. So how do we determine this error? We can actually then compare the single point calibration result against the multi-level calibration result. Here's an example. We compare the result of the single point calibration against the multi-level calibration. Now, depending on the calibration gas composition, the difference on each range can be different. So in this particular example, let's say we calibrate the GC with a calibration gas of 90%. What it does is then create a straight line to there, which is 90%. And what it does is, because it will have the same peak area between the 90% on the multi-level calibration and the single point calibration, there's not really any bias on methane component when we measure at 90%. But on another scenario, if we calibrate it at 60%, then there will not be any bias at 60%, because the single point calibration will bring a straight line to the 60%. But it will give us a bigger bias when we actually measure at 90%. So in this example, if we actually calibrate the GC with the 75% methane here, that means like we're not going to have any bias here. So if we operate somewhere in this tiny small area, tiny small range, we wouldn't see too much of a bias. But as we go further away from that particular calibration point, then we will have a bigger bias. So when the process gas is stable, let's say we have a process gas that 75% in methane, and let's say we have plus minus 1% variation in the process gas. What happened here, if it doesn't really matter whether we actually use the true function or the assumed function, because we will always run in the linear range. And this is why it's important to understand what kind of range we actually operate in our actual process. So when the process gas is stable, the calibration gas that we have need to be designed in accordance or similar as the process gas composition that we have to ensure that we operate in the linear range that the GC operates on. So this is basically the impact on the CV, and this is an example that we have. So if you see this particular example, this is actually two charts. So the blue line here is actually the data, mole percent, or sorry, CV data that is not implemented with the ISO 10723, or is basically the assumed function calibration result. But the green line is using the true function of the calibration result. So what we see here, we can see that the process gas average is around 85%, and we're basically use the calibration gas that is very, very similar to the process gas at that particular time. So as we can see that we don't really see any bias whatsoever. We do see a little bit of delta, which is a difference between the true function and the assumed function in the CV result, but it's not significant. Is what we're doing here, we try to change the calibration gas composition. So when we change the cal gas composition to go further away from the process gas, we basically tend to see a bias. So in this particular example, you can see that the calibration gas has been moved to 80% instead of 85%. So the impact of it is actually giving an error of 0.013% in the CV. Now, when we see this kind of error, 0.013% is actually negligible. It's really, really small. So we don't really need to bother ourselves too much about it. But the matter is basically how big of a bias that we can still accept in the system, not to bother about the calibration gas composition, or not to bother about performing the ISO 10723 test. The example here, I actually moved the calibration gas even further away. So we got a calibration gas here that has around 70% in methane, and as you see, any other components here, a lot of the components here is actually quite significantly different from the actual process gas composition. Now you can then see that the error that is introduced from the bias, from the non-linearity, is around 0.05%. In this particular case, it's actually over it by 0.05%. So when we talk about metering, what we want to do is basically to have a fair measurement. So any bias that we have in the system or systematic error needs to be corrected. So ideally, we don't really want to have this bias. One of the ways to design the calibration gas to be as close as possible to the process gas, assuming that the process gas is stable, and therefore we will always be operating within a linear range. Now, this is the simulation of the data when we have a calibration gas composition that you see here. So basically, we have a calibration gas composition that goes to 85% in methane. But what we basically simulate here is basically I simulated 10,000 data of all the possibility, of most of the possibility of combination of gases where methane varies between 60% to 90%. So as you can actually see here, when we operate on methane in 85%, regardless of what other components are, the other components, nitrogen, carbon dioxide, ethane, I basically put a range between 2% to 30% on nitrogen, 2% to 30% on carbon dioxide. I think I put 1% to 10% on ethane. It's quite a big range that we have on every other components in there. But every time we have methane operates at 85%, we can be sure that the error or the bias is less than plus minus 0.02%, sorry, 0.02 megajoules per centimeter cube. But as we move away from around 85%, let's say in our particular example just now, we operate on 65% or 70%, we then generate an error that is quite big. So we get to see the error that can go up to 0.08% when the methane is operate at around 70%. And even further away from it, like when we operate at 60%, the bias can actually go to more than 0.1 megajoule per standard meter cube. Now we don't really want that. Now this is why it's really important to actually understand where our gas actually operates on. What is the actual range of operation of our gas? Now changing the calibration gas composition will change this bias profile. So here's an example. We change the calibration gas to have 69.5% methane. As you can see, where we operate at around 70% here, where the calibration gases actually operate, then we basically have a bias that is pretty small. And also, if we see the overall error profile or bias profile, everything on the biases is basically less than 0.06 megajoule per standard meter cube, which can actually be acceptable across the whole range. Now, if we basically then operate in quite a massive range, then we need to understand the nature of the nonlinearity of our GC. And if we don't want to implement the analysis function inside the GC, then we need to ensure that the calibration gas is designed to ensure that the overall bias across the whole range will be lower than the tolerance that we basically set, the limit that we basically set. So what I'm going to talk about now is the ISO 10724 Part 1 2012. Basically, define two types of analysis of gas chromatography. So it basically says about type 1 and type 2. So type 1 analysis type means that any nonlinearity errors will be corrected by multiplying with the scaling factor. Now this scaling factor is actually the analysis function constant in there. So basically it will correct the any single point calibration into a multi-level calibration result. So this analysis function is implemented in the GC. So based on the ISO 10723 result, the constants that is generated by the ISO 10723 performance evaluation test is then implemented in the GC. So therefore, the GC automatically correct for any bias that arrive because of the nonlinearity of the GC. So when we operate on the type 1 analysis, the composition of the calibration gas doesn't really matter that much because it will correct for the whole range. So regardless whether your methane is 60% or 70% or 80%, it will give us the same function because it will correct for the whole range. Now on the type 2 analysis type, what it means is that any nonlinearity has to be included in the uncertainty budget. So this is why it's also important to understand what is the actual range of our GC. So if our GC operates, let's say, between 75% to 80% methane, we shouldn't do an evaluation test between 60% to 90%. The reason for that is because then we will actually look into the profile, error profile between 60% to 90%, where the bias that we're actually interested in is only operates between 75 to 80%. So what it does here, basically, the assume function is used, which is the single point calibration, and any errors that arise from the nonlinearity or the bias needs to be included as part of uncertainty. So let's say we have a bias of 0.05 megajoules per standard meter cube, or let's say 0.1% of a bias introduced by the system. So that 0.1% need to be added arithmetically to our uncertainty budget of the CV measurement. So we got the standard that specify all that, but I'd like to talk about a little bit the risk associated with this bias. Basically, what does it actually mean when we don't implement the multi-level calibration in terms of error that we actually looking at? So first of all, actually, some of the requirement. This off-gem here is basically one of the requirement in the UK, and basically it says that the purpose of calorific value determination is for the purpose of the Section 12 of the Gas Act, which is the law in 1986 that came out in 1986. So basically, any instruments that measure calorific value needs to have an uncertainty less than 0.1 megajoules per cubic meter, or 0.25% relative. Now, I would like to make a highlight the value here. So 0.1 megajoules per cubic meter is basically what we call maximum permissible error. So if the error on the GC goes beyond that, we should not use this GC for the measurement. But what we have been saying all this time when we analyze a lot of GC data, we see that GC is capable of much, much better than 0.25% uncertainty. In a lot of cases, we actually see that the GC uncertainty is pretty close to around 0.12% uncertainty. Basically, the requirement here that we also have is, as per the standard, the ISO 6974 standard, Part 1, 2012. And it basically say the primary calibration of performance evaluation should be carried out in the following situation. Now, the performance evaluation that it talks about here is actually the ISO 10723. ISO 10723 performance evaluation task that is to do with the non-linearity of the detector itself. So it actually gives you a suggestion that it needs to be done immediately following initial installation of the system, immediately following return to operation after major part of the system replacement, column, detector, valve. This all makes sense. And then immediately following return to operation after failure to pass the QA check of the system. For instance, this is like failed the performance evaluation test. So and also at the intervals that have been demonstrated to be appropriate for the application. So basically, it basically says that every 12 months or so in this particular example, we need to perform another ISO 10723 test. Now, although this all sounds really wonderful, but there's few limitations in there. The first limitation I find is that immediately part is not really as easy as it sounds. The logistic on making 7 gases available for the ISO 10723 performance test, and also on top of that, the resources to actually perform the performance evaluation test, it actually takes time. It also doesn't really help that some of the regulators, some of the regulations actually require that the test is done by a lab that has ISO 17025 accreditation. So resources is actually an issue. Now, the other issue here is that although it is an international standard, not many places in the world can actually perform the ISO 10723 performance evaluation test. To my understanding and knowledge, not many people, let's say in North America, are actually even aware about what the ISO 10723 standard is all about. And then places like Asia, Southeast Asia, Australia, Africa, not many people actually perform it. And a lot of people perform this test. The majority of people or the majority of operators that perform this test located either in UK or pretty much generally in Europe. So it's not really widespread in terms of the actual performance evaluation test that is done across the globe. When I talk about it, is that basically looking into the risk more deeply is because like a lot of people don't really have access to the performance evaluation test. So we need to understand the risk. Like, what if we don't do it? If we actually need to do it, then we need to make a provision to actually do it pretty much everywhere around the world. But if we don't have the provision on how to on doing the performance evaluation test, then we need to understand the risk. Now, what we know now is basically the risk of non-linearity errors can be reduced by designing a calibration gas that is similar to the process gas composition. Now, in this particular example, is very, very similar example that I showed before. I thought it's just nice to bring it back here. is that the bias due to the non-linearity is around 0.19 megajoule per centimeter cube, megajoule per meter cube, and it amounts to around 0.05% of bias. Now, this bias here happens because the calibration gas that we have is designed not as per the process gas that we have. On the average, the process gas that happens is around here. So if we design the calibration gas to be closer to the process gas, then we'll have a better bias. So now coming back to the system here, when we actually design the cal gas as per the process gas, is very, very similar. What we basically have is then no bias. So basically, by designing a calibration gas composition as per the process gas composition, it will reduce the bias itself. So when the GC is used to measure a large variation of gas, the risk from nonlinearity is higher, and this can happen in many different occasions. For instance, some platform that will utilize gases from two different wells, for instance, and maybe a GC that have stream 1 measuring data from well 1, and then stream 2 measures data from well 2 that have two different composition, or gas transportation company that have different entrance to the system. So it might have quite a big variation of the gas composition. So when we have quite a large variation of gas, we will have a higher risk from the nonlinearity. So what we need to understand is how big of a bias is then introduced to the GC by operating a type 2 analysis. So the type 2 analysis is the one that we basically don't implement the constant in the GC. So if we know the bias, then we can decide whether we need to operate in type 1, or we can just leave the bias and include that as part of our uncertainty in our uncertainty budget. So when we do have a large variation of gas, it is always recommended to operate using type 1 analysis in accordance with ISO 10724. So basically, any nonlinearity is then corrected by applying a constant. So we basically operate with a true analysis function rather than assume analysis function. Calibration gas is then to be designed based on the composition that will provide with minimum bias across the range, as we've shown you before on the charts in the simulation. When we have a range between 60 to 90%, when we have a calibration gas at 85%, when we then operate at 60%, we have a bias that goes up to more than 0.1 megajoules per centimeter cube. But if we change the calibration gas where methane goes down to around 70%, then our bias across the range only amounts to maximum 0.06 megajoules per centimeter cube. So we need to understand what kind of a function that we have, and then we can design the calibration gas that is best for that particular function for the operation range. So however, basically, if after performing performance evaluation tests, it can then be shown that GC bias plus uncertainty is negligible, which is like far below the limit, the risk limit needs to be defined by the end users and stakeholders to determine, although it's defined by the ISO 10974, and sorry, by the ISO 10723, but a lot of people are not aware about this. And it depends on whether people want to comply to a certain standard or not. So if you want to comply to a certain standard, then it needs to be based on that particular standard. But if like the fact that even the provision to perform the ISO 10723 is not even there, that means like it's not going to be conforming with the ISO 10723 standard, then we basically need to understand how big of the risk, and then we put a limit into the system, and then it's up to the end user and stakeholders to determine what is the risk limit. So if basically we know that the GC bias plus uncertainty is negligible, then I suppose we don't really need to perform the performance evaluation test. And this is all dependent on the risk evaluation from the end user itself. So here's some of the recommendation that I have. Basically, I'm talking about the overall globe market rather than places that have ISO 10723 performance evaluation tests easily available. So if the provision of performing ISO 10723 is not available in certain region, what we need to do first is that the calibration gas should be designed to be as close as possible to the normal operation composition. So where the gas composition is known to be unstable, let's say because of the wells, various different wells are being used to fit the gas into the GC, then we recommend that the ISO 10723 performance evaluation test to be done in the factory before the GC is actually installed on site. So therefore, we basically know the characteristic of the detector of the GC that we're going to use, and therefore we can understand whether we need to implement the constant in the system or not. So where the gas composition is stable, GC will operate in its linear range when cal gas composition is similar to the process gas composition. Now, so basically when we have a stable gas composition, we need to understand historically what is the actual range that we have and design the calibration gas based on the average data over a certain period. And therefore, we will ensure that the GC will operate in its linear range. On any other condition, perform as per the ISO 697 recommendation. So again, coming back to the recommendation, we need to do all that to be compliant to the ISO 697 However, if the risk of not performing the task is actually lower than the cost of the performance test itself, that means the risk of the bias is really negligible, then it's up to the end user for not performing the ISO 10723 performance evaluation test. And that basically concludes my presentation on the GC Surgery Session 5 about multi-level calibration and ISO 10723. Questions, then you can post the questions on our LinkedIn group. You can go to the LinkedIn and search for the GC Surgery group and post your question there, and I'll try my best to answer any of your question. So also, if you do have any question that you don't really want to share with anybody else, let's say some problems that you have on your own site that is that you don't really comfortable of sharing with everybody, then you can send me an email or send Jen an email in the following detail. Thank you very much for watching, and I'm hoping to see you on the next GC Surgery session. Thank you. Thank you.